I'm Pete.
I'm Stephanie.
You are hearing banjo music. The pitch is made possible by additive manufacturing.
Today on the show, we're looking at a 3D printed accessory for banjo players that's being made through metal binder jetting.
The Paige Pro Banjo Capo on this episode of the Cool Parts Show.
This episode of the Cool Part Show is brought to you by Carpenter Additive. The company's Powder Life solution is a combination of hardware and software technologies designed to help AM users manage their metal powders. Stay tuned after the episode for more on how the system works.
Welcome to the Cool Parts Show.
This is our show all about innovative 3D printed parts. If that's something you're into, subscribe to the channel on YouTube. You can also sign up for our all access newsletter to find out about new episodes even earlier. Today on the show, we're going to be talking about this accessory for banjo players. It's an assembly with two different integral 3D printed parts.
This is a capo for a banjo. It's developed by Paige Musical Products, which makes these high-end sophisticated capos for guitar players. And when the company, they wanted to offer something similar to banjo players, they needed additive manufacturing to get there.
So today we're going to get into how and why the components of this capo are now 3D printed. But first, let's talk about what a capo is and what makes this one so special. So a capo is an accessory used by players of string instruments, guitars and banjos. Its role is to sort of like hold down the strings to change the pitch of the instrument. And in a lot of cases, the capo is using some sort of like softer material like a rubber to actually sit against the strings. But with that solution, you don't always get even pressure, even tension across all of the strings. And it can also have some impacts on the sound that you may or may not want. So this capo has a little bit of a different design. So the two pieces that we're going to be talking about today are the yoke and the bar. And if you look at the bar, inside there's this slot with these little plastic inserts. There are four there, there's one for each string, and they sort of self-adjust against the instrument so that you do get even tension across all of the strings. This design was invented, developed by Brian Paige, who is also the founder of Paige Musical Products.
Seems like all the capos back when we started making capos were just kind of huge, bigger than they needed to be. Ours are smaller in size. And also you have total control of the tension. You have a screw that you control with your hand. And it's very important to control your tension when you're capoing, because if you have too much tension, you're pulling strings sharp. If you don't have enough tension, then you have string buzz.
So you can hear how knowledgeable Brian is about musical instruments, about fretted instruments. But the business that he started, it began as a tool and die shop, a machine shop. But Brian's a musician. He's interested in capos because he felt like he could do it better. And the evolution of his company's capo designs took the company through various manufacturing processes. Capos were made through machining, stamping, die casting, and then with the introduction of the product the company calls the Paige Pro for guitars, they landed on metal injection molding.
We wanted it to be stainless steel. It's like a lifetime. It's a really high-end product. And so we went metal injection molding because it's just very intricate, you know, a lot of intricate pieces in it.
So the guitar capo has a very similar design to the one that we have here. Some of those intricacies that Brian was referring to include the slot in the bar, the latching mechanism, some of the details on the yoke, and those intricacies led Paige Musical Products to metal injection molding, specifically to a company that specializes in powder metallurgy called Alpha Precision Group. Here is Dave Smith, the Director of Engineering for Alpha Precision Group, or APG.
So MIM was a great fit for the six-string assembly and the majority of the components within that assembly, because they are relatively small in size with really complex geometries. So we were able to form net shape almost all of the features required for the more complex components, which actually showed a drastic improvement over conventional methods of manufacture, whether it be machining or screw machining some of these components. So we offer the value of threads in an as-centered component, as well as significant undercuts that would be really challenging to get with conventional machining methods.
So that's metal injection molding, or MIM, which is kind of like it sounds. It is like injection molding for plastics, the way a lot of plastic parts are made, except applied to metal. The starting point is metal powder, smushed together into a mold to get the form, which is then sintered to finalize the part. It's done on equipment that is just like plastics injection molding. It has many of the same needs, notably the need for a mold, the need for a tool that is just like the part you're trying to produce. And that tool is a big investment. It's expensive. And so if you are going to go to market with a product that's going to be made through metal injection molding, you have to be confident you're going to sell enough units to justify and pay back the cost of that mold tooling. When it was time to introduce the Banjo Capo, Brian Paige knew there was a market there, but was there a large enough quantity of potential buyers that he could justify that mold? That was unclear.
The problem with the Banjo was there's just not the market. There's way more guitar players, right, than banjo players. You know, I knew about 3D printing, but I had no idea they could do it with metals like 17-4 stainless steel, you know, with the sintering process, you know, kind of like they do the metal injection molding process.
So the Banjo Capo was a new design that it incorporated some differences and a lot of upfront design for manufacturing DFM considerations. So it led very well to at least prototyping in the metal additive space. In addition to that, until it gains market share, we knew it was going to be lower volume. So not only could we use the metal additive technology to prototype, develop, work through the design with our customer, but also to support the low volume production until it gains market share and we can eventually tool up and metal injection molding.
So even though APG was already using metal injection molding for the parts of the guitar capo, the quantities needed for the banjo product tipped the scales towards 3D printing. Fortunately, this is also something that APG has experience with. They have a number of different 3D printing technologies that they use, and for the Banjo Capo, they decided to go with metal binder jetting, so specifically using the shop system from Desktop Metal. So similar to metal injection molding, you are building up a green part that you're going to have to sinter later from metal powder, but instead of using a tool or a mold to form the powder, you are developing the green part by literally depositing little droplets of binder across a loose bed of metal powder, building your part up that way layer by layer, and then extracting it from the powder, debinding it, and sintering it much in the same way that you would with a MIM part.
Binder jetting is a separate process. An additive manufacturing process has its own process considerations. APG is knowledgeable about that as well. To talk about the advance of the Paige Pro Banjo Capo into production through binder jetting, here is APG's manufacturing engineer for additive manufacturing, Joe Taylor.
The starting process is with the design. If the customer does not have a 3D model available, we will have to generate one, then create an STL file. Then that STL file goes into either a build slicing software or into a distortion predicting sintering software that we perform an FEA analysis on to predict sinter distortion. In either one of those softwares, we would create a live setter or design a live setter. From there, the print file goes into the printer. That's where the printing begins. Then from the printer, we go into a cure oven for a predetermined set time and profile. Then to depowdering to remove all the loose powders around the components. And then into sintering, and we have a complete part after that process.
Joe talked about sintering as a necessary part of the binder jetting process, necessary to metal injection molding too. In binder jetting, the 3D printed part bound together in a green state initially, and then it's completed through sintering in a furnace. And in that furnace, crazy things can happen, do happen. There is shrinkage, for example, but that shrinkage is repeatable. There's the potential for the part to distort at those high temperatures, but the distortion is predictable and controllable. And this is really a big part of the expertise that APG brings. Very familiar with sintering from other sinter-based processes that the company has been doing for quite a while. Stephanie, you mentioned how this bar is a particularly intricate part of the capo. Well, actually, in sintering, the challenging part is this yoke, because it has these arms that just hang out there, kind of suspended in space, and during sintering, those arms can deform. APG sees that coming, can predict that, control against that. In the case of a challenge like this, the solution is a device in sintering called a live setter.
The shrinkage for desktop metals is non-isotropic. It could be anywhere from 16 to 20% in X, Y, and Z. To mitigate that, or to predict that, we use a software called Live Sinter from Desktop Metals that runs an FEA on the part using the STL file and compares it back to the original or native CAD file, and then offsets the printed geometry to get close to that nut shape.
So once parts were printed, depowdered, and cured, they were also printed with their active setters or their live setters to be able to support that geometry in preparation for the sintering process. So proactively understanding what distortion is inherent in both processes as a result of high temperature sintering, led us to a place where once we had sintered components, it limited the number of iterations in additive and reprinting of additive components to provide acceptable parts that would assemble and function into the final capo assembly.
So APG needed to control shrinkage and distortion in the sintering of these parts. They were able to do that using some software tools, creating those live setters. Again, these are things that they're pretty used to dealing with on a daily basis. One of the more unique challenges, though, with this capo was the fact that it's a consumer product. This is something that a player is going to use. They're going to touch it, feel it on a daily basis. And so it needs to have good aesthetics. It needs to have a good surface finish. There were some things that APG did in both the printing process and the post-processing to make sure that this capo was going to look as good as it sounds.
Paige Musical is distinctive because this is a visual component, and binder jet yields a semi-rough surface finish. Printing orientation and sintering orientation is critical to minimize layer height or layer steps in the Z direction because these parts are highly polished after sintering. So we have to be cognizant of layer lines and part orientation. So on Desktop Shop, we have 3 options for layer height. We can do 100 micron, 75 micron, or 50 micron layer thicknesses. Obviously, with the decreased layer thickness, you add cycle time. For this project, we obviously picked the 50 micron layer height, and we knew what areas of the part were going to be critical and hardest to polish for the end use. So we kind of oriented that where the layer lines would be less pronounced. I will say that there was some post-processing that were needed on our end for some dimensional requirements, some coining, some squeezing of features that we actually learned from our MIM products for the 6-string guitar that we utilized in Additive.
One thing I really liked was the fact that we could get a batch of parts in, and then if we wanted to make a little change next time around, you don't have high tooling costs to do that. So you can kind of tweak things on the fly. The quantity, you don't have to order thousands of pieces, We've been kind of feeling out the market, and the only thing we've really changed is the bar. Like you said, the bar. You can pretty much change the bar and accommodate for a lot of different instruments by changing the bar radius.
That brings us to one other benefit of using additive manufacturing to produce the Banjo Capo, which is the variability of banjos from instrument to instrument, specifically the variation in the neck. The front surface of the neck, it might be flat, there might be an arch to it, like a gentle curvature, and the capo has to conform to it. This bar has to match that geometry of the neck, and as it turns out, banjos vary more than guitars do. Like Paige Musical Products didn't face this problem with its previous capo. But with the Banjo Capo, this bar needs to vary. Like here's another version, and it's hard to see, but there's a little bit of curvature there to match a banjo that has that much curvature. And other banjos could have a different radius than this. Trying to serve that need with molds would be impossible. There would be just no way to get a different mold tool for every different curvature of Banjo Capo bar. But with additive manufacturing, this is no problem. It is easy to serve every possible slight variation in bar that is needed.
You have radiuses on banjos from no radius flat to like a 7.5-inch radius on the fretboard. So the bar needs to match that. If you want even pressure, then when you tighten that down, it tightens all the strings simultaneously, with the same pressure.
So banjo players need to match the capo that they're using to their instrument. And there's a relatively high variety of banjos out there for a relatively small number of players. So this is an application with smaller quantities, but higher variety. And that means that additive manufacturing, binder jetting, is a better fit for these parts than other processes. This Banjo Capo is out there already, it's available, and they're already getting some good response. Here's Brian one more time.
Well, the biggest response, we went to a kind of a trade show, IBMA. It's an international band competition. There's young musicians that come from all over the United States there. They all seem to have this same banjo lick where they just bend the heck out of the strings. Normally, you bend strings with a banjo, and you have a conventional capo. A lot of times that string will pull sharp underneath the capo. And it was kind of funny because every musician that would come in there would do the same lick. And they couldn't believe that they could do that lick and the banjo would stay in tune, and it just worked. They couldn't believe the tone that they were getting from it.
I think we got this.
All right. This is the Paige Pro Capo made by Paige Musical Products. It's an accessory for banjos that allows users to change the pitch of their instrument by clamping down on the strings. The design was created, developed, invented by Brian Paige, and it's based on the design of a similar product for the guitar that's made through metal injection molding, but the components of the Banjo Capo are instead metal 3D printed.
Metal 3D printed for a couple reasons. One is because the universe of banjo players is smaller than the potential market for a guitar capo, but also because a banjo capo needs more geometric variation. This bar needs to vary to reflect all the different ways that banjos differ from instrument to instrument. Brian's company, Paige Musical Products, is a small manufacturer that faced a choice between metal injection molding and binder jetting, made two different choices for two different products. For more about that choice, our All Access members got to hear APG's Dave Smith go into more detail about these two different processes, the factors that play into deciding between them. If you'd like to hear that, joining All Access is easy. It's free. Go to thecoolpartsshow.com/allaccess to sign up.
Special thanks to Tim Poole, our banjo player for this episode. You can catch Tim playing with Pappy's Jam Band all around Kentucky and the greater Cincinnati area, and also follow the band on Facebook.
If you have a cool part you might like to see us do an episode about, maybe it is a product for a niche market and you thought about various different ways to produce it, we'd love to hear about that. Email us, coolparts@additivemanufacturing.media.
Play us out, Tim. Thanks again to our sponsor, Carpenter Additive. In addition to supplying metal powders, the company also offers services, software, and hardware to help AM users manage their powder. One example is the Powder Life System, a combination of cloud-based tracking software with hardware designed to make powder handling easier. Two key components are the Powder Life Hopper and the automated docking station. Luke Boyer, manager of Powder Life Applications, and Andrew Holliday, applications engineer, explained how the system works.
So today, when a user of additive manufacturing is receiving powder, they oftentimes receive it in either 5, 10, 15, maybe a 20 kilo bottle. But they're receiving pallets of them, and you're receiving 10, 20, 50, hundreds of these bottles. The user has to look and segregate and store them appropriately so the bottles don't get mixed up. And it requires a lot of lifting and moving and labor.
The components of Powder Life are all based around making powder management systems on the additive manufacturing shop floor easier to use for the operator, cleaner, as well as more traceable. 3 of those basic parts of Powder Life are our Powder Life hoppers, or our storage containers for powder. The second would be automated docking systems that allow material to be pushed in and out of machines with no human contact. And the third would be our Powder Life online software system that allows you to trace this powder as it goes through your shop floor.
The hardware, the software together just helps really streamline that and improve the final user's experience and let them concentrate on going from design to the part itself. Takes the headache of powder management out of the equation for them.
That brings us to one other benefit of using additive manufacturing to make the Banjo Capo, which is, don't touch it yet. I'm not ready to touch it. You keep touching it too soon. Keep your hands off the capo.